Venumadhav, and Teja is visiting us from Caltech, where he joined in 2010 as a Fulbright fellow. And his advisor there is Chris Hirata. And his research in the past has been around periodic fluctuations during recombination, 21 centimeter cosmology, and also Newton's laws. And today he'll be telling us all about the 21 centimeter line and how we can use them to prove our primordial.
Alright, I'll begin. I'd first like to thank Prayush for hosting me. And yeah, so I'm a graduate student at Caltech, and today I'll be talking about my work on 21 centimeter cosmology and how it can be used to measure magnetic fields in the early universe. So I'll begin by introducing my collaborators on this topic. So Antonia and Abhilash are grad students at Caltech along with me, and Vera is a postdoc at the IAS, and of course my advisor Chris Hirata. So since this talk is connecting a couple of slightly disparate topics, I'll have two introductions. One to the idea of cosmological magnetic fields, and one to the use of the 21 centimeter line in cosmology. And then I'll move on to talking about our mechanism and how it enables you to measure magnetic fields. And then I'll briefly talk about detectability. And if I have time, I'll tell you about work we are currently doing on using similar methods to measure gravitational waves or tensor modes at the same epoch. So let's begin. Right, first, magnetic fields. So as we all know, magnetic fields are spread over a wide range of length scales and strengths in the universe. Depending on who you talk to, it might be somewhat of a dirty word like magnetic fields, but they're there. And so this shows that their strengths vary over like something like 30 orders of magnitude, all the way from magnetars at like 10 to the 14 Gauss down to okay, a few times 10 to the 14, 10 to the 15, right, Gauss, down to magnetic field in galaxies and clusters, which has been shown to be of the order of 8 to 10 microgauss. But what is below there is somewhat more uncertain and like sort of like the wild west of cosmology, right? Because we do know that there must be some magnetic fields on very large scales, but what they are and how they are distributed and what their strengths are is really not known. And there are really tantalizing hints that they might be down here, which is like 10 to the minus 16 Gauss or lower. And just for reference, the most precise magnetic field ever locally measured has been like 10 to the minus 14 Gauss by the gravity probe B experiment, but not measured, but isolates it up to that level of accuracy. So if we think about extragalactic magnetic fields, there are two schools of thought on how these could be produced and on what length scales they exist. So the first is cosmological, right? So they're seeded at very high redshifts, and then they propagate forward in time, and they're there on very large scales today, and because it's cosmological. And this has like some like one bad thing about this is that since naturally they dilute away as the universe expands, you need to produce them at large strengths for them to be seen today. But it naturally produces them on large scales, and you can have your pick of your favorite method to generate them. Like some of them could be reheating, like post-inflationary reheating, and then you could also generate them in phase transitions in the early universe, like during the electroweak transition and during the quark-hadron transition, depending on what you look at. And there are also hints that you could generate them post-recombination because of slip between baryons and photons, right? And the second school of thought is astrophysical, right? You produce them on smaller scales within local galaxies, with the first galaxies which are created, and then you kick them out. So this will naturally produce them on smaller length scales, and all these mechanisms share that they are the so-called Biermann battery, right, where vorticity of the motion of charged particles is converted into magnetic fields. And the signatures, so the distinguishing features, as I've tried to emphasize, is that they have different length scales and they also have different redshift dependencies. So this is the current sort of state-of-the-art sort of constraints on magnetic fields, which I've taken from the science paper by Neranov and Vogt. So this plot shows the strength of the magnetic field versus coherence scale, or this scale over which they typically vary, right? So first thing I would like to point is, so it goes all the way up to micro-Gauss, which is what we have observed, and the length scales vary from the diffusion limit to the horizon scale at when they're produced. And so this is all the clusters which have been measured, and these are the bounds which have been put upon this extragalactic magnetic field by the non-observation of the Faraday rotation of the CMB. And the red lines represent theoretical estimates for what you could think the various mechanisms I listed earlier could produce. So the dashed ones are like sort of inflationary ones which generate them on really large scales, and these other ones are all the like phase transition sort of stuff. You can see that the CMB is nowhere near constraining most of the space, and the dashed lines are these dashed lines are constraints which are lower bounds which were placed by looking at the non-observation of GeV cascades from Fermi observations of TeV blazars. But there are a number of uncertainties in that, and depending on who you ask, it could either be that bound could either hold or not. But
so you said earlier that we know that there have to be very large-scale magnetic fields, we just don't know how strong they are. That statement based only on this Fermi line, basically?
So on the observational side, the strongest motivation is the Fermi one. On the theoretical side, it is a channel in which you can dump energy after inflation, right? But yes.
So that's basically that's basically an argument for why should they be there.
Yeah, so I would say the Fermi one is a stronger one, but regardless of whether that holds or not, it's an interesting question to ask. So if we ask what a wish list would be for a probe of these primordial magnetic fields, you can come up with these things. So you first want to be able to isolate the effects of redshifts. So like things like this non-observation of halos around blazars, right? So that is affected by the integrated magnetic field along the line of sight from the blazar to us. So it can't really distinguish whether it is really far back in time or now, as far as until the redshift quasar. The second thing is, of course, you want it to be sensitive to really low field strengths. And the last thing is you want to be able to recover coherence lengths. And what I'm going to show is that in principle, the 21 centimeter transition has all these abilities. So let's move to the 21 centimeter transition. So not everyone, I guess, works on it, so I'll just briefly introduce it. So the 21 centimeter transition arises because of the splitting of the ground 1s state of the hydrogen atom, because of the interaction of the electron spin with the nuclear spin. So because it's a spin-spin interaction, this is a very weak transition, and the splitting corresponds to 1.4 gigahertz in the rest frame, which is in the radio band. And one important feature which I want to emphasize is that the excited state is a triplet. That's going to be very important in what I'm going to say. So throughout this talk, whenever I make a statement, I'll give both a classical version of the statement and a quantum mechanical version of that statement. So the quantum mechanical fact that it's a triplet is the classical analog for that is the fact that the arrow of the net spin can point in any direction. So both of them are the same statement. And yeah, so just keep that in mind. The second thing is, as I said, this transition is a spin-spin transition, and it's a so-called magnetic dipole transition. So that is saying that if you want to jump from the lower to the upper level or vice versa, you'll have to flip a spin and not move a wave function around. So because of this, it's very slow. And the inverse width is around, the inverse width is like 10 mega years, or the spontaneous coefficient is, this value, which is few times 10 to the minus 15 inverse seconds. So this is very long-lived, and you should also keep this in mind because this is going to be very important in what I'm going to talk about. So if we try to make contact with what people usually use in this field. So in this field, everyone likes to measure everything in terms of temperatures. So one important quantity to keep in mind is the spin temperature, which parameterizes the relative occupancy of the upper and the lower levels of the transition. So it's given by this, right? And what this means is that the spin temperature is the temperature of a heat bath with which these atoms will have to be in equilibrium to have the populations that they do. So the spin temperature is set by whatever is causing the transition, whatever is predominantly causing the transitions at that moment. So the spin temperature evolves through the universe, evolves through the ages as various processes become important or unimportant. So this plot shows the evolution of some temperatures with redshift. So the redshift is on the x-axis and the temperatures are on the y-axis. So the black line is the CMB temperature. As we know, it goes linearly with redshift. The red line is the kinetic temperature, which is the Maxwell-Boltzmann temperature corresponding to the thermal motion of the hydrogen atoms. And the blue line is the spin temperature. So this is cut off at like 30 or something because I generated it using CMB fast, 21 centimeter fast, which is optimized for reionization. So if you go to very high redshifts, the important, beyond like 100 or so, the important processes are actually collisions, where what happens is these hydrogen atoms, if they're occupied with a spin temperature which is different from the kinetic temperature, every time they collide, once in a while, one of the spins flips, and that energy goes into the motion of the atoms. So eventually, this will set the spin temperature to the kinetic temperature. So that happens at very high redshifts, where both the CMB and the kinetic temperature coincide. Yeah, so the blue line and the red line are for like a fiducial model of reionization, which one thing I should emphasize is the blue and the red line, exactly where they dip and curve depends on astrophysics, and that is not like this. So this is not necessarily what is going to be there, but in general, that they will have this transition is it's true. So and then as the universe expands, the kinetic temperature falls from the CMB temperature, and then it enters but collisions also become less important because it's diluting away and they just can't find each other very easily. So then the most important process becomes stimulated emission, where the very small width of the transition gets augmented because of the CMB photons, and that sets the spin temperature to the temperature of the CMB, which is this epoch, which is the sort of nearing the end of the dark ages. And then the next epoch is when the first ionizing sources turn on, and they emit ionizing photons, but they also emit Lyman alpha photons. And what these Lyman alpha photons do is they cause an indirect transition between these two levels. So what that means is you go from f equal to 1 to 0, or the triplet to the singlet, by going to 2p and then coming down. So it's a two-step process. So normally two-step processes are really weak, but the Lyman alpha transition has a really, really high optical depth or cross section. Because of that, it can do this. So this is known as the Wuthusen field effect. And what this does is it tries to set the spin temperature back to the kinetic temperature. And then in general, because these ionizing sources are also emitting X-rays, they heat up the IJM and the kinetic temperature shoots up. So that's shown here. So there is a lot of astrophysics going on, but there are these generic features in the spin temperature. And right, but what is actually observable is the brightness temperature, which is related to the spin temperature but not the same. So the brightness temperature measures how as the CMB passes through this neutral gas. We have a question? Okay. Yeah. So as the CMB passes through the neutral gas, it either gives energy to the gas or takes away energy from the gas depending on the spin temperature relative to the CMB temperature. And the brightness temperature measures how much energy is dumped into the CMB or taken out of the CMB. So if the spin temperature is less than the CMB temperature, you see it in absorption, and vice versa, you see it in emission. And the output brightness temperature is given by this, where so it's given against the CMB, right, and it's redshifted. And it's given by this thing where so this 26 millikelvin is based on just atomic physics, and everything else is where the astrophysics comes in. And as I said, it comes through a radiative transfer solution. So the properties of the gas influence the brightness temperature through all these coefficients, right? So the density, the velocity gradient, the neutral fraction, and the spin temperature, all of them set the optical depth of this transition and indirectly influence the output brightness temperature. And this is the root of why this transition is useful for cosmology, because so this shows the fluctuations in the brightness temperature as a function of frequency or redshift. So it starts with the lowest redshift or highest frequency here and goes all the way back to the highest redshifts there. So first is at low redshifts, there's just not enough, there's not a lot of signal from the IGM, and that is because it's fully ionized almost. So there's just not enough neutral gas, so that X1s factor kills it. And then as you go through reionization, you start seeing a signal. And this signal from the epoch of reionization, it has these fluctuations because of what I said, that the input fluctuations in the gas from, which have their root in inflationary fluctuations, right? They modulate the optical depth. And through this modulation, they introduce this modulation in the output brightness temperature, which many future radio arrays want to measure. And the reason why this is so exciting and it will be so important is that this is a 3D map of these primordial fluctuations, right? Because there you also have the redshift axis. So unlike projective measures like the CMB, this gives you more information. But it's also relatively simple microphysics, unlike a galaxy distribution, right? And the second thing is the CMB is diffusion damped on small length scales, but this is not. So because of both these factors, you get access to a lot more modes, and this is why people are so excited about 21 centimeter. So what I'm going to tell you today is a potential application of this, the 21 centimeter, measuring the 21 centimeter fluctuations, which goes beyond what these motivations have. So I'll move on to the main topic, but before that, if there are any questions, I can. Right. So before I introduce the method, I would just like to note certain things which will be helpful in understanding it. So this picture shows how atom in the singlet state, which is represented as F equals 0, absorbs an input electromagnetic wave which is coming in from the left. So since the transition from the singlet to the triplet is a magnetic dipole transition, so the so-called transition dipole moment aligns with the magnetic field of the input wave rather than the electric field, right? But the fact that it aligns is, I'd like you to note that. And the second thing is, you can also think about this as this is the time reverse of the emission process, right? So the same thing will be in reverse when you look at emission. Right. So this picture shows a cloud of neutral hydrogen atoms floating around in the IGM, immersed in an isotropic bath of 21 centimeter radiation, which is coming at it from all sides. So if they all started out in the singlet state, then once they get excited to the triplet state, the transition moment has no preferred orientation, right? Because it's isotropic. So that is the classical picture corresponding to the quantum mechanical fact that all the three upper levels are equally occupied. Right. Now I'm immersing these. I'm looking at the same cloud of hydrogen atoms which have now been immersed in an anisotropic 21 centimeter field. So so here the axis of the anisotropy is parallel to the plane of the board, and so there are hot spots in these directions and a cold ring around the equator. And what you see is that I've put all of them here, but basically what happens is the transition moments have a tendency to align in the plane of the cold spot, basically up or down, or left or right, depending on what you call. But the probability of that is greater than the probability of them aligning in this way. Whether they are up or down, you can't say, but the fact is that, so the mathematical way of saying that is that you get a non-zero expectation value of f rather than f itself, right? But so the quantum mechanical corresponding thing is that the triplets gets unequally populated. So for the geometry of this particular figure, the m equals -1 and 1 states get occupied preferentially corresponding to the m equals 0 state. But if the quadrupole is reversed, the other thing happens. So before I move on, I'd just like to talk about how we describe this fact in our analysis, right? So the usual 21 centimeter calculation, which looks at the spin temperature, is just sensitive to the net occupancy of the three levels, and we have to go beyond that. So the way we do that is we follow the density matrix of the hydrogen atoms. So if there are n levels, then there's an n by n density matrix describing the state of the system. So here there's a 4 by 4 density matrix within which we are looking at the 3 by 3 part, which looks at the subspace of the excited levels. So the spin temperature is just given by the trace of this density matrix, right, which is the net occupancy. So the diagonal elements represent occupancies of the levels, and the off diagonal elements represent correlations between the different m's. So
Like A, B, singlet.
Yes. Yeah. So usually you call them A, B, C, D, or in the literature, but yeah, I'm just calling them -101 to emphasize that it's a magnetic quantum number, right? So the differential occupancy which I talked about in the previous slide is measured by this quantity which I've suggestively called P20, which is the difference of the sum of the occupancies of the m equal to -1 and 1 and twice the occupancy of 0. So this departs from 0 if these two are preferentially occupied compared to this, right, and only this. But so the geometry of the previous figure was with the axis aligned along the quadrupole, right? If you chose a general axis, what happens is these other elements of the density matrix start getting populated. So that is described by these other numbers, which are suggestively again called P2 to 1 minus 2, which are built out of these off diagonal elements in the same way like this is built out of the diagonal elements, right? So there is there's a lot more structure to this than just the spin temperature, right? So it's somewhat suggestive that I've called it P2M because it's basically I'm saying that this is a quadrupole, just like the exciting quadrupole, right? So now that I've told you about the effect of anisotropies, so where are these anisotropies coming from? So a natural source of these anisotropies you could think of is the CMB, but the CMB is not resonant with the 21 centimeter transition. Its peak is blueward of the transition. So there's a lot of photons in the CMB, but they're not going to excite this. So what is naturally going to cause this transition is the same things which cause the brightness temperature fluctuations, which is the density fluctuations in the neutral gas. So this I've written out the optical depth of the neutral gas, which, it's around 1% for redshifts of 10. And again, you have all these astrophysical factors. And what I want to point out is that it depends on the velocity gradient. It depends inversely on the velocity gradient seen by the atoms, right? Because that sets how much time they remain within the line. And so here I've shown the same cloud of neutral atoms sitting inside a plane wave of large-scale structure. So it's a growing mode of large-scale structure. So the dark band is an overdensity. So along the axis of the plane wave, the velocity gradient seen by the atoms is the Hubble rate, but it's corrected by the peculiar infall velocity, which is causing the Fourier mode to grow. So, so that I've shown this here, and perpendicular to the axis of the quadrupole, perpendicular to the axis of the mode, there is no peculiar velocity, and all you see is just the Hubble rate. And because the optical depth depends inversely on the velocity gradient, the atoms see a hot spot along the direction of the wave vector.
So the degree to which the local velocity effects dominate over the CMB anisotropies, do they grow with decreasing redshift? If you go to a higher redshift, you're saying that the anisotropy of the CMB is not as important as the velocity of the local effect. I'm just asking how redshift dependent statement is that?
Yeah, so actually towards the end of the talk, I'll briefly talk about how the CMB affects it. So yeah, I calculated that, and the point is that at the point where the CMBs, has the point where the CMB becomes resonant with the 21 centimeter transition has not occurred yet, right? Because now it's at 150 gigahertz, and it's at even higher frequencies before.
So if you put in 200 kilometers per second for the velocity, how often -3 multiplied to get 10 to the -5 for this?
Yeah. This.
So why do you say it's so much bigger?
No. So the CMB anisotropy is 10 to the -5, but it's off resonant.
But you're thinking about, for example, 30 shows that the spin temperature is in equilibrium with the CMB, meaning all it sees is the CMB anisotropy. I mean, I guess I'm missing what you is referring to, but redshift 30 in your curve, the equilibrium is given by just the CMB and is fully coupled, right?
No. So it's coupled to the CMB, but not by stimulated emission, right? Wait. No. I didn't get your question. I'm sorry. It is coupled by stimulated emission against the CMB.
Yeah.
So so that sets the spin temperature, but wait.
So in the sense that in a quadrupole field, the fact that in the monopole field, which you calculated, you concluded that the n turbulent over n singlet is equal to is given by the CMB and not by anything else, meaning it's reached equilibrium. So the temperature field, if there's enough time to do that, CMB doesn't change it. The CMB quadrupole is completely invariant in time, or almost invariant in time. So why wouldn't you have said the same thing with the CMB, that the equilibrium temperature you see depends on direction, and therefore the spin, it just calculates the temperature.
Yeah. So at the end when I talk about gravitational waves, I'll show how that I have calculated that, and it's a couple of orders of magnitude below this. I'll show that. Right. Yeah. Right.
So this effect is bigger than 10 minus 5.
Okay. No, there are a couple of questions here. Okay, I'll get to that one second. Right. So now if you take that they're aligned, right? So what's the consequence? Right. So the first thing is that this alignment is present in the standard calculation too, but it was not appreciated, and it's not important for the purpose of estimating the brightness temperature at lowest order, because the lowest order brightness temperature is an order tau calculation. So in other words, it just looks at how much energy has been taken out of the beam, say, if you're looking at it in absorption, rather than what has happened to the atoms which processed it. While you would really see these extra aligned moments only at order tau square, because these aligned moments will de-excite and emit their own quadrupole, right, which would be something which will come at order tau square. So normally, for the purposes of estimating the brightness temperature fluctuations, this is completely negligible. But because of the fact that it's associated with these moments, I'll show that it has a very interesting effect when you immerse them in a magnetic field, as you might expect. Right. So before I get into that, I'll just briefly again tell you how we describe these anisotropies. So the way we do that is we look at the input phase-space density seen by the atom and decompose it into spherical harmonics and look at the quadrupole part of that, right? And we solve the radiative transfer problem again. And so the output quadrupole is a function of the input quadrupole as usual. So this is the usual order optical depth calculation, right? And now you have this extra term, right, which comes at order tau square. So this extra term is because of the aligned moment, so to speak, right? And as I've said, without a magnetic field, it's completely negligible. So if you immerse them in if you immerse these atoms in a magnetic field, so here I've shown the same geometry as earlier with the wave vector pointing, in the plane of the board, but I've added a magnetic field which is pointing out of the plane of the board. So one thing about these atoms in a magnetic field is they precess, right, these moments, intermediate moments, and the handedness or chirality of the precession does not depend on whether it is pointed up or down. So macroscopically, these aligned atoms all precess with the same orientation or handedness. So this is the classical statement which corresponds to the quantum mechanical fact that this magnetic field causes a Zeeman splitting of the three levels, right? So you have this characteristic ladder structure, but normally for such weak magnetic fields like what's important for this, the Zeeman splitting would be completely negligible if you thought of looking at it for just looking at the frequency splitting of the line. Right? Normally you would think you would compare the Zeeman splitting to the level gap itself and say it's split by X%, right? But here the Zeeman splitting is so faint as to be comparable to the lifetime of the level rather than the width, rather than the level's gap itself. So in a lab you would never measure this, but it's somewhat special that we can measure this because we have, because in cosmology we have access to the 2-point correlation function rather than just the 1-point correlation function or just the intensity or what you see.
People have measured this, right? People have, we heard a lecture last month to measure this.
Of splitting of the order of the lifetime?
Splitting of the 21 centimeter Zeeman effect. That's the Zeeman effect here, right?
Yeah, so the Zeeman effect of the 21 centimeter has been used to measure the local magnetic field in the galaxy. I'm talking about from redshifts of reionization and before.
Nothing can be measured there. If you had a magnetic field in the lab of the same order of magnitude as you expect, then you won't be able to measure.
Oh, that's 10 minus 16 Gauss. Yeah, you would not measure that.
So I'll sketch how you can measure that. So this shows the same plane wave as earlier, except it's oriented in a general direction. I've added an observer who is represented by this radio antenna looking up. So the line of sight is along the upward, right? So as earlier, you have these aligned atoms which are created because of this effect I talked about, and they de-excite and emit this secondary quadrupole which is order tau square and really faint. Now you put them in a magnetic field and this quadrupole precesses slightly, right, depending on how long this atom stays in the excited state, and that changes the intensity this observer sees for assigns at this particular atom. And if you think about the geometry for a second, whether the intensity increases or decreases depends on which quadrant this wave vector lies in. So if the wave vector lies in the first or third quadrants, it sees more of the blue part, so the intensity increases, and if the wave vector lies in these two quadrants, it decreases. So through this, essentially you're looking at how the magnetic field breaks the isotropy of the space these atoms live in, and you can only do this in the 2-point function. So this is something unique to cosmology, so to speak, right? And I'm just illustrating this in this because usually in this business people don't talk about the 1-point function at all, right? So these curves have the same geometry as earlier, except they are showing contours of equal power for the 2-point correlation function in momentum space, right? So you have kx, ky, kz. The observer is looking up here, right? And so the figure A shows the intrinsic brightness temperature fluctuations, whose contour is spherical, because it obeys the isotropy of the background fluctuations. Figure B shows the effect of so-called redshift space distortions, right, where the redshift you assign to a particular point, right, it's biased because of the local peculiar velocities. And what that does is, in real space, usually it scrunches the correlation functions, or in Fourier space, it stretches them out along the line of sight. And that is what this shows. And this figure shows the same geometry, except I've added a magnetic field out of the plane of the board. And what that does is it rotates the correlation function slightly around the direction of the magnetic field. So if you add the effect of the if you look at the change from here to here, you have basically broken the symmetry around the line of sight. So around the line of sight seen by an observer. And so there are two effects which you can use to measure, right? One thing is the direction in which the isotropy is broken. That tells you the direction of the magnetic field. And the second thing is the amount to which it's broken, and that tells you the magnitude of the magnetic field, right? And usually the sort of things, so people write estimators for the redshift space distortions, which just look at k parallel and k perpendicular, right? So that is sort of blind to this, because that is compressing all the information orthogonal to the wave of sight, to the line of sight, into one number, which is k perpendicular, sorry. And one thing I wanted to just point out for people who are not familiar with it is that the passage from here to here, which is the redshift space distortions, are the main thing by which people hope to do 21 centimeter cosmology with, because the intrinsic fluctuations themselves also heavily dependent on astrophysics, say, but the passage from here to here is cosmology. Okay, so let's briefly look at what is the typical magnetic field which you would measure by something like this. Right, so that is set by the lifetime of this excited state, or how long they have to precess before they fall down. So let's assume that the lifetime is set by stimulated emissions mainly. So so the lifetime is the inverse of the spontaneous emission rate, but it's boosted because of the presence of the CMB, and you get that it is around 10,000 years at a redshift, or 13,000 years at a redshift of 20. Right? And the rate of precession is the gyromagnetic ratio, which is 2 times 10 to the 7 inverse seconds per Gauss. So if you put these two things together, you get this thing precesses it has a natural magnetic field scale of 10 to the minus 19 Gauss. Right? So in effect, the thing which I said, you have to note before, is that it has a very long lifetime, is what sets the scale of the magnetic fields you can measure. And what sets the coherent scale of the magnetic fields you can measure is the maximum k you can resolve, so that for which you look at the isotropy breaking, right? It looks at magnetic fields on scales larger than that. So I've described, sort of this method and the mechanism in some sort of maybe semi-simple language, but it's a very involved calculation, and I've shown the various pieces here. And so the cosmological calculations are shown in green, and the atomic physics flavor calculations are shown in red. Apologies for colorblind people. And
naive question on the previous slide still. Go back one slide before this.
okay.
Yeah, so the precession, I mean, if I choose my up and down coordinates in the parallel to the B instead of parallel to the field lines, because B in fact is still parallel to your field lines anyways, then I would have concluded that the triplets are eigenstates under B and don't possess. Right? So that term doesn't possess. However, now you're going to say, because I observe in a direction which is perpendicular to the B.
Yeah. So for any, if you forget the observer, right, and think of the most natural coordinate system for the atom, which is say choose the direction of the magnetic field, say, right? Yeah. So then you only change the direction which is perpendicular to B. So in other words, you are only sensitive to magnetic fields in the plane of the observer sky, or the component of a magnetic field in the plane of your sky.
So you're saying the precession in the, if I took my coordinate system to be in the B field, then my 3M's are eigenmodes, they don't possess at all, they stay there. And then the precession comes because if you're in a superposition of two of such states, they rotate at differential rates given by the energy change, and if I project onto another axis, I see a rotation, I guess.
Well, so the thing is, the fact that they precess, if you choose your axis of, in the direction of B, then they're eigenstates, but they're not. So you also want them to be unequally populated, right?
You want them to be unequally populated.
And that happens, so the equal or unequal population is decided by the direction of the wave vector k. So you want k to not be along B.
Right.
So there are B, K, there are three vectors in this problem if you think about it from a larger perspective. One is B, one is the wave vector, and one is the line of sight. I'll show you what like it looks like. Right. So the atomic physics calculations, which to the best of my knowledge were not done earlier, they're quite interesting in fact. And so for that we have to look at, because the usual 21 centimeter calculation for the optical pumping strength and the collisional transitions all assumed isotropic populations. And if you want to look at the time scale over which the moment de-excites, it will be the same order, but it's something which will enter this size of this effect. So you can calculate the effect of the lifetime of this excited triplet, the anisotropic triplet, because of optical pumping and collisions, right? And in the end, of course, the cosmology calculation, the output quadrupole and the resulting change in the brightness temperature is what will constrain. So this is just showing that what you see is dependent on all these atomic physics, but it's relatively simple atomic physics. So I just wanted to show the result which we have, which is this monolithic formula for the brightness temperature change for linear regime density fluctuations with low optical depth and in steady state. I'll just show you what each part corresponds to, right? So this is first written in the coordinate system with the z-axis along the magnetic field. So this is the standard order tau calculation. This is the 26 millikelvin brightness temperature fluctuation, and this k dot n whole square is the elongation in the line of sight or redshift space distortion, right? And this is the order tau square piece, which was not calculated earlier because it would have been small anyway. So this is the emission of the secondary quadrupole, which is small, right? But this is the interesting part, with the magnetic field in there. So these factors show how you break symmetry about the line of sight, right? And this is the xb is a coefficient which measures the strength of the precession relative to radiative de-excitation. and then you have all this polluting atomic physics, which we have calculated, but they're encapsulated by these nice coefficients.
So is it always cold spots where the field is not pointing in the direction that you're looking at?
No, I didn't get your question.
So so you say there's no effect when the field is in the direction, but when the field is not in the direction, does it always make it colder, or it goes in either direction?
No, sir.
The temperature fluctuation.
Yeah, so when the magnetic field is in the line of sight, then there is no change.
Right. But when it's not, it could be either hot or cold.
Yeah, so that depends on which wave vector you're looking at, right? Like, which quadrant. So for certain quadrants, it will become hotter. For certain quadrants, it will become colder, right?
When you get a polarization signal or a power from this?
Yeah, you do get a polarization signal, which is FE, which I've also calculated, but that is not the important thing you're going to do, because measuring E mode polarization from this is really hard.
Well, okay, then I'm missing it, I guess. So if you have enough polarization of your spin states, such that you change the population parallel against the field, then because the emission, the polarization fraction is equal to the amount of polarization you gave to the atoms.
You're going to get order delta tau square of linear polarization too from this.
But then it's the same size.
Yes.
So it's easier to measure because you don't have to deal with the K anymore.
No, but yeah, the impression I got from talking to the 21 centimeter people is that polarization is incredibly dirty.
Sorry?
Incredibly dirty.
Dirty.
Right. I mean, I have that too, but in principle that has the same thing, but its polarization is really hard, like linear polarization. Right. So just some intuition is there. So there was this monolithic formula, but I wanted to show how it looks in weak and strong magnetic fields. So in the weak field, this is the change in the brightness temperature for per change in the magnetic field, right? And in the strong field, you have this thing. And what I wanted to point out was in this weak field, right? You have this geometric factor, right, which corresponds to what I said earlier, that it depends on which quadrant you are orthogonal to B, depending on the line of sight. Right? And the second thing I wanted to note is, for fields which are really strong, this effect saturates. So you cannot make out the magnitude of the magnetic field anymore. But from what I said, that from the direction in which the isotropy is broken, you can make out the direction of the magnetic field. So that is shown by these geometric factors. So even if the magnetic field is much stronger than anything like these scales, you can still make out where it points in the plane of the sky with this. Right. So I mean, this is like a neat theoretical thing you can do, but the question is, will this be measurable? So for that, we are choosing to look at something like an SK array, right, and trying to see what is its constraining power on these magnetic fields. And it's somewhat hard to say what SK parameters are, given that it doesn't exist yet. But with some educated guesses, we think we're looking at their whatever documents they have and trying to see, because basically which Fourier modes you can measure is heavily dependent on the survey geometry and the survey parameters, right? And which redshift range you can integrate over is dependent on that, and that will all of that will affect the sensitivity. So at the preliminary level, at least, we can try to see what you can do with that. And the idea is to back out the magnetic fields you can measure using that. And it's we're currently doing that. And at least, so for this part of the talk, I would like to end by saying that there's really exciting physics in there in the 21 centimeter transition if you get these high resolution maps, which I was told I should be optimistic, so I'm optimistic about it. but it's really interesting. And the second thing is, so this is a preliminary calculation of the signal, right? And to go from there to detection is a very big step, and for that you have to study about, I wrote foregrounds thrice because it's that important. And the second thing is uncertainty in the astrophysical parameters, like the Lyman alpha flux. If you nail that down, that's going to help a bit more. And the other questions you could ask is, if you wanted to just look at this, what would be the array design you would use? Presumably you would want more, you would want greater access to a lot of modes at a few length scales rather than a large number of them. The last thing is, if you went even further, you could think, because this has redshift information, right? You can distinguish the case of a uniform magnetic field just diluting away versus the case of a magnetic field which is being produced and fluctuating on small length scales, depending on what k vectors your survey gives you access to. But there are all these interesting questions which you can think about after this.
Would you see the emission of our galaxy? Because why not?
You need, so basically the change in the brightness temperature depends not on the magnitude of k, but only on the direction of k. So the sensitivity goes roughly as the volume in k space that your thing probes, and you would want a large, and for this thing to easily be, for this thing to lie within this simple physical regime, you want your mode to be, you want your fluctuations to be linearly sourced, right?
Well, I mean, it may be hard to predict what it is, but you've got gas, the optical depth, so the actual T brightness of our galaxy is like 100 Kelvin, so it's 1,000 times brighter.
Yeah. So there is a second reason why it is also really hard, because the density of in our galaxy is really high, right? So the density of the IgM at these epochs is incredibly low, and in such densities, your predominant channel for de-excitation from the triplet to the singlet is collisional and not radiative.
I mean, our galaxy?
Yeah. It will radiate a bit, but it will be collisional. And I don't know if you can, if you have access to, Fourier modes kx, ky, kz, if you look at a small patch of the galaxy.
I get a little confused about how the detectability of this depends on, three angular scales: the size of your beam, the coherence scale of the magnetic field, and the size of your bubbles that are being.
Well, this is in the pre-reionization epoch, right? So there are no, you would want to minimize these effects like these bubbles.
I see.
You want this to be cosmological, basically.
So then you know what the power spectrum of the delta is. Okay, but then how does it, so you require a coherence length of the magnetic field larger than your beam, basically. So you can,
yeah, and you require the coherence length to be larger than the wavelength of the modes whose isotropy is being broken. Right? If it is smaller, then it will average itself out. So I still have a few minutes, so I'll talk about gravitational waves if you would like to hear that, which is something which grew out of this work, but it's very different, but it's also very interesting, though a bit more speculative, I would say. So the first thing, so while doing this calculation, we were worried about what happens. So, there are these atoms which are sitting in the IgM for a really long time, and we are looking at really faint Zeeman splittings, and we were of the order of the lifetime. So what if their isotropy is already broken because of the CMB, right, or something like that. So we wanted to look at what happens if you immerse these atoms in an anisotropic CMB. And what that does is it shifts around the levels. So this is what is, so the CMB's frequency is much higher than the rest frame 21 centimeter frequency. So what this is in quantum mechanical language, this would be a dynamical Stark effect. Or if you wanted a classical picture of it, so you would have, the electron spin and the nuclear spin, and the CMB is a really fastly oscillating field, but which mainly the electron sees and not the nucleus. So the electron is going to wiggle around, and that's going to change the energy of the state, but it changes it differently if the CMB is anisotropic for different orientations of the spins. And what we showed was that the change in the energies, of the levels are much smaller than, like a couple of orders of magnitude smaller than the magnetic fields, like of 10 to the minus 19, it's Zeeman splitting itself. But what is an interesting thing is that the change in the energy levels does not have this ladder form, but rather it has this up, down, up. It's a quadrupole form, which you might have guessed because it's a quadrupole, the CMB, while this B field is a pseudo vector, right? So you have this up, down, up configuration. And now if you think about what such an energy shift does to aligned atoms, right, which I already talked about, like how they get aligned, it turns out that they get oriented. So what that means is, earlier you had a non-zero expectation value of fx, fy. Now you get a non-zero expectation value of f, or in another manner of speaking, one of these gets more populated than the other one. And when that happens, they emit circular polarization. So through this related but very separate effect, there should be a very small amount of circular polarization of the 21 centimeter signal from the epoch of reionization. And what is using the same methods, I went through the whole thing and calculated the observed circular polarization. It's going to be really small, and why is that? Because the circular polarization, it requires both to align the atoms, which depends on the density, and it requires the CMB to cause this thing to get oriented. So you have the CMB quadrupole. So it's a product of this density in the CMB quadrupole. So if you think about a change to the transfer function, right? So it's millikelvin times 10 to the minus 5. So it's going to be like 100 nanokelvin sort of circular polarization, which is really small, but there's nothing else which will make them circularly polarized, while there are many things which will make them emit intensity, right? So it's worth thinking about. And an interesting thing which I'm currently doing is that if you look at this circular polarization, so one way of thinking about it is the circular polarization emitted by these atoms traces the quadrupole they see, the CMB quadrupole they see. And the CMB quadrupole will have one contribution from scalar modes, which is aligned with the wave vector, right? Scalar modes have a quadrupole which is aligned with it, and one from tensor modes, which is orthogonal to the wave vector, or the hot and cold spots are orthogonal to the variations. So if you have a really good V map and a T map, you can correlate them and project out the part orthogonal to the wave vector and that would trace the tensor modes. So of course, if you woke me up from sleep and asked me, is this how you would measure a tensor mode, then probably this is not the simplest way. But this is a very new thing. And the second thing is, because of this long lifetime and things like that, this can be sensitive to incredibly small amounts of, like incredibly small tensor to scalar ratios of something like. So this is.
You're trying to measure the L equal to 2 tensor modes at that redshift.
Yeah.
So there are like 5 such modes in the sky.
So in principle this will be what you call influenced by tensor modes on all scales, which the atom sees, but tensor modes dilute away as they enter the horizon. So the main important tensor mode which will cause this will be horizon scale tensor modes. But
Zeeman also circularly polarizes.
No, so there is no circular polarization in the classical, if you have a magnetic field, you generate.
You don't measure it, right? That's how they measure when you're telling me the Zeeman is circular polarization. Yeah, so that's the standard procedure.
No. So because in the standard thing, basically these two are equally occupied. The circular polarization you emit cancels out in the standard calculation.
If you have a magnetic field.
Yeah, if you have a magnetic field, the magnetic field causes V.
No, if you have a standard magnetic field and these are equally occupied, you won't emit V.
No, they're not equally occupied as much of energy, right? So what you do is you look at different wavelengths.
Yeah, but here the splitting is so small, you're not going to see it because of that.
And nanokelvin. I'm just saying.
Yeah, you're not going to see it
I'm
because
saying
of
that
that.
people have seen it in 21 nanometer at much more than nanokelvin at the back.
Yeah, but that is for magnetic fields which are, so I see what you're getting at is that, so you're looking at large Zeeman splitting and you're preferentially populating one of them. We can work this out later if you want, but I think that in the standard calculation there will not be any V emitted by the atoms.
You measured it, one of the calculation question is being measured. What is named Heilis? No, Heilis, right?
Well, I think what you're saying is that the magnetic field is so weak you can't measure the Zeeman splitting, so you can't see it and stuff. I guess that's your argument, right? I mean,
I
the
still.
way to measure the Zeeman splitting is that the transition from the M-1 mode and M+1 mode both are circularly polarized.
So there, I think what you're seeing is that these two modes are, so the energies are really different. So the population becomes unequal just because of the fact that the energies are really different. But here the energy splitting is so faint that it's not going to cause that.
You're saying that the levels splits because equal population, but the transition from -1 and from +1 end up at a different frequency.
Mm-hmm.
Okay, no, the population is the same, but the transition shifts to a different frequency.
Mm-hmm.
And it's the reason why.
Oh, so okay. I see what you're meaning. You're saying that essentially what's happening is, if you observe the splitting of the frequency, each one will be circularly polarized at a different frequency. But here the splitting is so faint that you will mix them both into one frequency, and you won't see circular polarization.
That's all the true. I'm saying the reason why we use circular polarization for Zeeman splitting is because the splitting is very, very small, even for these micro-Gauss fields, and it's very, very small, much less than the width of the line. Right? So that's already a fact. Even today, even locally, that is a fact. And then just note that because it's systematic, the splitting is a systematic effect. So even though it's very, very small, it gives you a left-wing, right-wing change of polarization, for which you can, because nothing else is circularly polarized, you still see a net effect, even though it's very, very small.
So what I'm saying is, for a 10 to the minus 19 odd Gauss magnetic field, in the same way in which it produces circular polarization for the micro Gauss magnetic field, you will get circular polarization at slightly different frequencies, which are really small, really separated by tiny amounts, but you won't resolve them within. So you will add them together and say that it's unpolarized, is what I'm saying. We can talk about this in more detail, but yeah. So, but if you want to continue discussing, I'm happy to do that. But yeah, if you have if there are any other questions, I'm happy to answer them. Okay.